Hey Pre-Calc, I hope you're doing great today. Today we're going to continue to look at models. So we've spent some time looking at what happens as a wheel spins. Great application of trigonometry and writing trig functions. Today we're going to look at something called simple harmonic motion. It's when something is just simply going up and down. And I'll give you a little setup here. For our problem, I'm going to show you a quick video just demonstrating what that looks like, and then we'll get back to the problem. So here's the situation. We've got a ball that's hung from a spring attached to the ceiling. Okay, so let me draw the ceiling here. I'm going to draw a spring. Make it look all zigzaggy kind of. Something like that. Okay. And we've got a ball attached down here. Okay. At rest, the ball is 10 centimeters below the ceiling. So we're going to say from there down to there is 10. The ball is then pulled an additional 5 centimeters down and then released. It takes 2 seconds to return to the point of release. I'm doing this really slow, and it's okay. It's not super realistic, but we're just going to say it takes 2 seconds to return to the point of release. Assuming no friction or air resistance, write and graph a function that gives the distance of the ball from the ceiling with respect to time. So I want to give you a visual on what this actually looks like. So I found this YouTube video here from MIT that I think is really helpful. So let's watch this together. Well, that was beautiful, wasn't it? Really cool illustration here of that can going up and down, spraying the paint, and we see a nice sinusoidal curve. Now, the sinusoidal is a word that I haven't used yet, but a sinusoidal curve just describes any curve that's a wave that could be modeled with sine or cosine. Really, we can choose either one because we know they're just horizontal translations of each other. But we see that nice sinusoidal curve. Okay. So what's going to happen here as we pull the ball down and release it, it's going to go up and down. And I want to graph here a function where this is time, and that'll be in seconds. And then this up here for the y-axis, what do we want to graph here? That gives the distance of the ball from the ceiling with respect to time. Okay, so this is going to be in centimeters. And be careful, it's the distance the ball is from the ceiling. So when we grab this at time 0, okay, we have pulled it down and we release it. So what is the distance the ball would be at time 0? Well, when it's resting, it's at 10 centimeters below the ceiling. We've pulled it down another 5 to let go. So the distance the ball would be 15 centimeters from the ceiling. Now it's a positive 15 because I asked for the distance of the ball to the ceiling. Now if I asked for the position with respect to the ceiling, then you could make an argument that that should be a negative 15. But here, this is a key word here, the distance the ball is from the ceiling. So it starts at a height, a distance of 15 centimeters from the ceiling. Then what happens? Where does it go? Well, we know it's going to go up, so we know the distance has to go down. Does the distance to the ceiling ever become 0? Well, how does a spring work? If I pull this down another 5 centimeters, okay, the ball would now be down here. When I let go of it, what's going to happen? Well, it's going to reach a height of 5 centimeters above where it started. Those are going to be the same. That didn't look really the same, but There we go. If I pull it down 5, it's going to come up 5 above where it started. It's not going to rocket and go beyond that, and it's just going to go back and forth, okay, between the two. Now, I did make the statement here, no friction or air resistance. We know if we really did this on a spring, what would happen? It would be going up and down, and then it would just slowly become less and less and less and end up at rest. If there's no friction or air resistance, in that video from MIT, they created something as pretty close to that because it was not slowing down at all. It just kept continuing. We will look at examples where we do have friction and air resistance slowing it down. That's called damped oscillation. And we'll get to that, but not in today's video. All right, so it starts a total of 15 centimeters from the ceiling. Then what happens? Okay, what's the next thing we know? Well, we know that it's going to take 2 seconds to return to the point of release. That's going to be our period, isn't it? We'll put a 2 there, and we've got to be back at 15. Now, what are the other points that I know? Well, where is it at 1 second? Well, if it starts here, it goes all the way up and back down in a total of 2 seconds. So where is it at 1 second? 1 second, it's going to be right up here. I wanted that to be green. Okay. So what is the position at 1 second? How far from the ceiling are we? Well, we are a total of 5 centimeters from the ceiling. Now, what happens halfway between where the ball is here, down at 15, and there, up at 5? Where does it pass through? Eventually, it goes back through 10, through its equilibrium. So 10 is right there. This looks like it's just getting a little high here. I should use an actual graph, but there we go. At half a second, it's right there. And at 3/2 of a second, it's right there. And we would draw the curve to look like that. So sketching the curve, I think, is a really helpful place to start. Instead of just trying to jump in and write the function, I think graphing it is a great place to start. All right, so now let's write the function here. Okay. Think about what we need here. I'm definitely thinking starting with cosine because it starts at the highest point and then goes down. So let's use a cosine function. What's our amplitude? Well, here's our midline right there. What's the furthest that we get from the midline? That would be 5. Cosine of. Now we need to determine what the period is. And our period is 2. So we know that period for cosine is 2 pi over b. So we're going to set 2 equal to 2 pi over b. So I know 2b equals, right, 2 pi, dividing by 2 on both sides. B is pi. So I'm going to have pi times t, okay, to change my period. So we've got our amplitude of 5. Okay, we've changed our period to be 2, so our b is pi to do that. Last thing we have to do is we have to translate this up. Our midline goes from 0 up to 10, and we've got a plus 10. Okay, there's our function. Okay. Now let me do a little twist off of this one. Kind of in the way here. If the ceiling is 3 centimeters high, write and graph a function for the height of the ball above the floor as a function of time. Let's see here. Well, what I'm going to do is I'm going to grab this. Let's take a picture of my work here that I've already done. Oops. Let's see if I can't put that in our new problem. Lights, thank you. There it is. All right, now let's shrink this down here a little bit. Okay. And let's draw in the floor. This is not to scale. Okay. So we know that the distance, okay, that the ceiling is from the floor is 9 meters. Now, we're working on centimeters over here, so we're going to have to change that 9 meters to 900 centimeters. And like I suggested on the previous page, let's start with the graph and then write the function. This is still time in seconds. This is our f of t, which is our height now off the floor, which is in centimeters. So the question is, what height does it start at? Okay. Well, it's starting a total of 15 centimeters underneath the ceiling. Remember how we started here at 15, but now we're 15 below the ceiling, which is actually a height. If we're 15 centimeters underneath the height of the ceiling, which is 900, that would be what? 885 centimeters. Okay. Now what happens when we release this? Well, it's going to go up, isn't it? Okay. It's going to go up, okay, come back down. We know it needs to be back where it started at 2 seconds. 2 seconds, it's back to 885. Where is it at 1 second? Well, like we said before, it's all the way up to the top of its motion at 1 second, which means that is now at a height of what? Okay. Well, from there all the way down to the floor is just 5 centimeters short of the height of the ceiling, so this is 895. Try to squeeze that in here. My spacing wasn't very good. So at 1 second, it's all the way there. Now, where is it halfway in between? Well, halfway in between, it's back to its equilibrium position, which is 10 meters underneath the ceiling, which would be at 890. So our midline for this one now is 890. Spacing was not great on this. Okay, so at half a second, if it's at 890, and at 3/2 of a second, it's at 890, and now we have this. So the question is, how are we going to write the function for this one? What's our amplitude? Our amplitude is still 5, isn't it? Okay. Are we still using cosine? Okay. Well, I hope when you look at this, you just recognize that this is our cosine function that's just been reflected. So it's upside down. So let's make that a negative and still use cosine. So -5 cosine. Our period is exactly what it was before, which is 2. So our b is pi. And now we have to slide up to our midline, which is now 890. So this is the function that gives the height of the ball above the floor. Okay, so the first function was the distance from the ceiling. This was the height above the floor, which would be the same as the distance from the floor. I could ask you to write a function that gave you the position from the ceiling, so you could use negatives and so on. But this is our function. I like that one. That's pretty good. Now, you could use a sine function if you wanted on this one. Notice, if you did a phase shift of 1/2, you could slide it over and then do a sine function. You could have done the same thing on this, except now you would have had to reflect that sine function starting here and going down. We know that there's so many different trig functions that we can write between sine and cosine to match up the graph. This would definitely be my choice for this one, although sine could also work if you translate it a phase shift of 1/2. So that's going to wrap up this video. In your next video, you're going to look at an example of daylight hours over the year. All right, thanks for watching.